So hello students, welcome to Unit 3 of Explainable AI. So in this session, we are going to explore one of the most exciting and practically relevant topic in modern AI. Can you guess it? Yes, see the slide, real world mapping of explainable AI concept. So by this end of this video, you will clearly understand how explainable AI is applied in real life scenarios. So which tools and libraries are used and why it matter more than ever in today's technology driven world. So let's get started. Okay, now move to the next slide. Okay, before we dive deep, let me walk you through what we will be covering today. Okay, at the session. So we will begin by comparing interpretable with explainable algorithms. So because these two are often confused. So then we will look at the important tools and libraries used in XAI. After that, we will explore the key model types, tree, rule, and ensemble models. So then we will move to the post-hoc explanations and visualization techniques. So the focus throughout this session will be real-time student understandable use cases. So every concept I explain will have a real-world connection. All right. Let's begin with why. So why explainability matters? So let me ask you a simple question. Imagine you applied for a bank loan and the AI system said rejected. So would you accept that without a reason? Of course not. That's exactly why explainable AI exists. So AI decisions directly affect the human lives. A doctor need to trust a prediction before the prescribing treatment. A bank must justify why the loan was rejected, especially under the financial regulation. So a teacher need a student wise insight to understanding learning gaps. So laws and governance in many countries now require the AI system to be explainable and fair. So here is a real classroom example. Wait, I'll show you. So here is the real classroom example. Why was this student marked as a slow learner? If the AI can't explain its decision, teachers can't trust it. So explainability builds that trust. So this is the core motivation of behind everything we study in the XAI. So see this slide, real world application domains. Now let's look at the where explainable AI is used in the real world. As you know, main part is healthcare. So AI models help the diagnose diseases. So doctors need to know why a model flagged a patient at a high risk, as a high risk. XAI provide that diagnosis justifications. For banking and finance, regulatory bodies like RBI require banks to explain credit decisions. XAI helps ensure compliance. Education, in an education, AI system analyzes the student performance with XAI educators can understand which factors affected a student's grade and intervene appropriately. So then business managers and stakeholders. For the business, the managers and the stakeholders need the decision transparency. XAI helps the organization make AI-based decision that humans can audit and understand. In a governance, so government applications require fairness and accountability. So XAA ensure no demographic bias goes undetected. So across these industries, it is also used in autonomous vehicle and then virtual assistant, customer support, then gaming. So the across industries, XAA is no longer optional. It is a requirement. Okay, what is that? XAA is a no longer optional. It is a requirement. So this is the domain wise we need. So now let's talk about the tools and libraries you will actually use when implementing XAA. The first one, SHARP. So it stands for Sharply Additive Explanations. So it tells you how much each feature contributed to a prediction. Feature mean here input. So it works globally across the world, a whole model and locally for the individual predictions. Then second one is LIME. So local interpretable model agnostic explanations. So LIME explain individual instances by building a simpler local model around that prediction. And then ELI5 model debugging, which means explain like a IMF5. A great tool, model debugging. It shows which feature are pushing the prediction in which direction. Then Captum. So developed by Facebook. Okay, already you know Meta. So Captum is not especially, specifically used for the deep learning explanations, especially for PyTorch models. So then scikit-learn, the most widely known ML library, which also support the tree visualization, allowing you to see the decision path very clearly. So these 5 tools form the core XAA toolkit. We will see them in action as we go forward. Now we come to the types of model used in the XAA. Let's cover the 4 important ones. Decision tree models. So decision trees are the most naturally interpretable models. Okay, they follow a tree structure. From a root node, you follow the branches based on the condition down to leaf nodes that give the final decision. So the path from a root to leaf is a human readable rule. This makes it is very easy to validate, debug and explain. So they are widely used in education, mainly for the students' performance and healthcare, in a particularly diagnostic system. Okay, they are the widely used in the education for identifying the student performance, in the healthcare for finding the diagnosis system. Okay. Rule based model. So these model work using the if then condition. Okay, so very similar to how an expert thinks. So for example, if a marks less than 40 and the attendance less than 75 percentage, then the grade equal to fail. So they are based on the expert knowledge, making them fully transparent. So easy to audit, easy to modify and commonly used in expert systems for a medical diagnosis and legal advisory. Then ensemble models. So ensemble models like a random forest combine the multiple base models for better accuracy. So while they are less interpretable than a single decision tree, so they do provide the feature importance scores. So telling you which feature influenced the outcome most. So this gives a partial interpretability, not a fully transparent, but a useful for understanding what matters to the model. Okay. The scoring models. The scoring model assigns the numerical decision score to each input. So this enable easy ranking and comparison. For example, a student academic score is computed based on the weighted criteria. So they are the simple, transparent and heavily used in credit scoring, which in banks, and academic performance in evaluation in the education. Now we move to the one of the most important concept, post-hoc explanations. So what is post-hoc? The post-hoc mean after the fact, right? So the model first make a prediction and then we apply the explanation technique. So without changing the model itself. So this is especially valuable for black box model. So it's like a deep neural network, the models that are powerful but not naturally interpretable. So post-hoc methods improve the transparency, then support the debugging, build the user trust. So let me walk you through the main techniques. Sharp provides the both global overall model behavior and local the single prediction explanation. So Lime, it explained the individual instances using a local surrogate model. So GradCam used here specifically for vision models, which mean for image classifications, to show which region of an image influenced the decision. Then PDP. PDP is nothing but partial dependence plots. So visualize the trend of a feature effect on the prediction. Anchors. So generate the rule-based explanations. It's like if age less than greater than 30 and the income greater than 50K, then approved. So visualization techniques. Visualization is a critical part of explainability. Let's look at how we visualized AI decisions. So heat maps and activation maps, right? So heat maps is highlight the important region in an image or data. Salenzi map show how the sensitive model is to each input feature. So listen, the heat map highlight the important region in an image or data. So Salenzi map show how the sensitive the model is to each input feature. So activation map reveal which neurons fired is in response to the input. The GradCam is used specifically powerful for CNN, convolutional neural network models. So it shows exactly which pixels influence the classification. So these visuals dramatically improve the human understanding of what a model is seeing. Right. The feature importance. So the feature importance tells us which input variable is matter most to the model. So this help remove the irrelevant inputs, improving the efficiency and improve the model transparency, support fairness analysis, detecting if a model is biased towards a particular feature like a gender or age. So it also simplify the decision logic. So then case-based reasoning. The technique explained the decision by showing the similar past instances. For example, so the loan was approved, it is similar to 95% of previously approved the cases with the same features. So this aligned very naturally with human reasoning. So we understand things better when compared to examples we already know. So it is widely used in medical AI and legal AI systems. Clear? So to counter these challenges, we can optimize our models, reduce the decision tree depth. So keep the tree simple and interpretable. Remove the redundant rules, which mean they simplify the rule-based model, right? So merge the similar condition. So it reduces the complexity. So it improves the clarity and the speed of the explanation system. So it reduces the overfitting so that the explanation generalized well to unseen the data, right? So these are the optimization strategies. So let's now look at some advanced but essential XAA concept. Okay, simplified models. So simplified models using the fewer features and rules leads to. So easier human understanding, faster model execution, better generalization, and improved explainability overall. So the goal is always same power, uh, same power, but simpler explanations, right? So this technique, concept-based technique, right? This techniques separates the meaningful, right, from noise. So it uses the labeled supervision to identify what each neuron represent. So it also assigned the one concept per neuron for clarity. It reduce the bias and improve the transparency. So this is very useful in deep learning where the neurons are otherwise uninterpretable. So when the dimensionality reduction, when the data has many features, we reduce the dimensions to preserve the most important patterns. So it remove the noise and improve the efficiency. So enable visualizations of high dimensional data. So the techniques like PCA, principal component analysis, are commonly used here. Okay. Finally, we convert the high dimensional data to 2D or 3D using the technique like TSNE or UMAP. So this help reveal the natural clusters and trends in data. So it detect the outliers. So it enhance the data understanding and it also support the better decision making. So these visualizations are a powerful communication tool between the data scientist and the non-technical stakeholders. So, all right, let's quickly recap what we covered today in Unit 3 Real World Mapping of Explainable AI. So, we understood why explainability matters in real world domains. We explored application areas, healthcare, banking, education, and governance. So, we studied the tools SHOP, Lime, Li5, Captum, and Scikit-learn, and we covered the model types, decision trees, rule-based, and ensemble scoring. We learned about post-hoc explanation techniques. We saw how the visualization aids explainability. We addressed the challenges and how to optimize. We touched on advanced concepts, concept-based reasoning, dimensionality reduction, and clustering. So remember, explainable AI is not just a technical concept. It is about the building trust between the humans and the machines. So as future AI engineers, your job is not just to build the accurate models, but the models that the people can understand, trust, and use responsibly. Note that not is not just to your job is not just to build the accurate models, but the models that people can understand, trust, and use responsibly. So thank you so much for hearing our lesson. If you have any question, feel free to reach out through the WhatsApp via. So thank you. Thank you all.